But all of these parity sequences fall into fairly many infinite families given by regular expressions. For example, 0, 1, 1, in this case 0, 1, 1, 0, 1, 1, followed by many 0, 1, 1, followed by many 1s, or 1, 0, 1, 1, followed by many 1s. So the computer completely empirically guesses the regular expressions. So you give it a certain ansatz, regular expression, and it looks at all the conceivable regular expressions that may show up. Still empirical, still experimental. But now, once again, by induction, you prove that these regular expressions in the parity sequences are all the things that have to be. Once again, by induction, because this is parameterized. So you look at this and you see, suppose I have something that starts like this. How is it going to continue? Then you use what you already know, the inequalities, and you can prove it by induction. So this is now phase 5. Express in closed form the two last numbers of such a trajectory. Now that you have these finely many regular expressions, remember the rules depend on even and odd. You have a parity sequence. So each rule is a matrix, a 2 by 2 matrix. So you can compose it and have powers, and you can express a typical element in the sequence x of n minus 1 as a certain explicit expression in the initial conditions, and m1 and m2, the parameters in irregular expressions. Since it is a cycle, x of 0, x of negative 1 must be x of n. And x of 1, the first must be the last, and the two first must be the two last. So you have two equations, and if you have more, you can compare them. So you have the initial conditions A and B, and the parameters M1 and M2 for the regular expressions. You solve them! Not you, the computer! The computer also. The computer automatically generates this set of equations, and right after, automatically solves them. Most solutions will give you A and B and M1 and M2, not integers. But since we know that A and B and M1 and M2 are supposed to be integers, we can discard lots and lots of options. And the computer does it. At the end, you get all the cycles that you initially conjectured. So all the phases of the strategy plan. The plan itself is still devised by humans. Very smart human. Let me give credit again. Jerry Ladders, Edward Grove, Candace Kent, and Amal Amle. They had beautiful plans, but then they wasted 2 or 3 months carrying the plan by hand. Instead, I wasted 2 or 3 months teaching my computer, in other words, programming the plan into a computer. And 2 or 3 months wasted doing it by hand, or 2 or 3 months wasted the computer, you think, we are even. But I told the computer. But once the computer learned how to do it, it has much more patience than what they did. They had a lot of patience. So my computer did many, many more analogs. Instead of only 16, it considered 256. And if I would have had more patience and entered in half an hour, I could have even millions of cases. But enough is enough. It still takes some effort to change the input file. So I stopped at 256. So my computer proved 144 new Collatz type identities. Ladders et al. Only proved 12. And using the same method, once it was told to the computer patiently did it. But still I have to make a confession. The success rate is not 100%. It's roughly more than 50%. So in the original thing there were 16 possibilities of the class, and they only did 12. And there's still 2 cases or 4 cases that are wide open. You're welcome to look it up. So this strategy, the way it's stated now, is not guaranteed to always work. It only works in some cases. But even 144 out of 256 is more than 50%. So if I were greedy, I could have published, my computer published 144 different papers. Each of them is a highly non-trivial result. But of course, I'm honest, so I only had 1 paper in my website. I have 144 different papers, but only published in my website.
When you say it doesn't work, that means the computer says it just keeps going.
Oh yeah, I don't know it doesn't work. Of course, you have to have a patience. You tell it, only go to slightly inside the complexity. It's very possible if my computer would have been bigger or been willing to try it out instead of doing other things, putting in my processors to let the computer work for a year. It's very possible. At least some of them would also be doable. Of course. It's not doable. Of course, you have to. But what's nice about it, it's not a priori decidable. You take a gamble and it's a luck of the draw. So here's an example of one computer-generated lemma 6 by rerun. So this is the inequality one. Okay, it's hard to see. Never mind, you can go to my homepage and search for Collatz et al. And you get it. But here, this is all this paper. This is only one out of the 144 theorems. And then gives them comes the lemma. So it's all online. So that's an example that I believe should be emulated. If you have a good idea, try to teach it to the computer. It's even good for you. And you know the best way to learn something you said is to teach it to others. So even the act of trying to teach it to the computer, network programming, will enhance your own understanding. But also once the computer really understood, not understood, but knows, never mind understood, knows to follow your plan, then it can do much, much more than you can ever as a patient. So then we conclude with a rather pessimistic note. Paul Erdos is really an endangered species. He was a human problem solver. And he was a great optimist. He famously believed that every nice statement has a so-called proof from the book. And the reason not every nice statement, like the four-color theorem or Fermat's theorem, do have to date a proof from the book, is that because humans were not smart enough or lucky enough to find it. By being an optimist, Paul Erdos believed that every nice statement should have a proof from the book. Unfortunately, it was probably wrong. I'm almost sure that the four-color theorem and possibly Fermat's theorem and possibly Poincare conjecture do not have proofs from the book. Most nice theorems have no proof from the book. And Kurt Gödel even proved it formally. In addition to proving that there exist statements that have no proof, he also proved that there exist false statements that do have proofs, but the proof is very, very, very long. So even Kurt Gödel, he did give an example, but he proved, in fact, that most false statements, which Erdos would call elegant, do not have a short proof. You do not have a proof from the books. So we have to be realistic. And it's very nice that there exist people like Andrew Wiles and Grisha Perlman who can still prove by human means difficult problems. But sooner or later, we run out of these people. And sooner or later, we have problems that are much, much harder than the Poincare conjecture or Fermat's theorem. And for this, our only hope is to teach the computer how to prove theorems. Not completely in the AI way, by completely emulating a human, but with an interaction between humans and computers. Find out a strategy, very, very generally, and then teach the computer how to execute this strategy. And I believe that we will all learn how to use this computer-aided methodology. We can achieve much more. Thank you very much. Be glad to answer any questions in private. Thank you.